Hello everyone, let us see next example of Fourier series chapter. Find the Fourier series of fx is equal to under root of 1 minus cos x in the series in the range 0 to 2 pi. And second question, sub question is prove that 1 half 1 by 2 is equal to summation over n 1 upon 4n square minus 1. Let us find out first the Fourier series of this function. In this range, the Fourier series is given by fx is equal to n by 2 plus summation over n an cos nx plus summation bn sin nx. Call that equation number 1. Not a naught is equal to 1 upon pi integration 0 to 2 pi fx dx. Put the values function here under root of 1 minus cos x. Now we have to solve this integration. For that we have one formula for sin square x is equal to 1 minus cos 2x by 2. Therefore 1 minus cos 2x is equal to 2 sin square. Now we want 1 minus cos x, half of the angle. That's why 1 minus cos x is equal to 2 sin square x by 2, taking half of the angle on the both side. Put this value here, we get 2 sin square x by 2. Now root 2 take outside of the integration and square root will cancel. It's sin x by 2. Integration of sin is it's minus cos x by 2 divided by angle derivative is 1 by 2 should be divided, and from the limit 0 to 2 pi. Now these two come to the numerator. Take this minus outside. 2 root 2 divided by pi and this minus cos, put the upper limit 2 pi, 2 gets cancelled, cos pi minus lower limit cos 0. We know cos pi is minus 1 and cos 0 is equal to 1. Therefore it's minus 1 minus 1. Now again minus gets cancelled. It's plus minus 2 into 2 plus 4 root 2 upon pi. This is a naught. Now consider an. An is 1 upon pi. An is equal to 1 upon pi integration 0 to 2 pi fx cos nx dx. To put the value of integration fx is, by sorting this fx is under root of 1 minus cos x. Directly we can write down root 2 or 2 sin square x. Okay, or under root of this is root 2 sin x by 2 and cos nx as it is dx. Now take this root 2 outside and use sin a cos b formula. For that we have to adjust 1 by 2 because 2 sin a cos b formula we have sin a plus b plus sin a minus b. This 2 is not here, that's why we have to take this 2 on the adjust side. It becomes 1 by 2 sin a plus b plus sin a minus b dx. Now to calculate integration, take this 2 outside. This root 2, 1 root 2 gets cancelled, 2 remains 1 upon root 2 pi integration sin, take this x outside of this bracket and multiply, cross multiply with this we have 1 plus 2n by 2, again sin 1 minus 2n upon 2 into x dx. Now take the integration of sin is minus cos into this angle divided by derivative of this angle should be divided, that is this term, this is a constant with respect to x, 1 plus 2n by 2. The rest of the terms as it is, minus again sin integration is minus cos of this angle divided by its derivative should be divided from the 0 to 2 pi. Now take this 2 to the numerator and take this outside and minus also on the outside the bracket. This take this 1 upon 2 comes to the numerator, take the outside out of the bracket. It is common to both term and again minus this terms as it is. Now take this minus also outside and all the term as it is. This becomes plus both the term. Now put the limits 2 pi in x first, upper limit cos of this is x is equal to 2 pi. By putting 2 pi, 2 gets cancelled, answer is only 1 plus 2n into this pi upon this as it is constant, plus again 2 pi here, 2 gets cancelled, this in angle into pi upon 1 minus 2 pi. Now minus lower limit we have to put x is equal to 0 everywhere. Cos 0 we know, again it is 1 and now cos 0 again 1, therefore 1 upon 1 plus 2n plus 1 upon 1 minus 2n. Lower bracket, lower limit bracket complete, whole integration complete. Now we have to solve this integration. We know cos of, take this pi inside, pi plus 2n pi is minus cos 2n pi. We are using this formula, cos of pi plus theta is equal to minus cos theta. Cos of pi minus theta is again minus cos theta. Both terms are same. These are the formulas. Okay. Therefore, it is minus cos of 2n pi. This is theta. Again, it is minus cos of 2n pi. This is again theta. Minus, take this minus inside. Minus 1 upon 2, 1 plus 2n minus this term. Now again, we know cos of 2n pi is 1. Therefore, it is 1 minus 1 upon this. This is again minus 1 upon this. 1 upon this, 1 upon this. Okay. Now, this term and this term are same. 2 times minus 2 times 1 upon 1 plus 2n. Again, this term and this term are 2 times minus 2 upon 1 minus 2n. Take this minus 2 outside of this bracket and minus minus gets cancelled. 2 root 2 upon pi. 1 upon 1 plus 2n upon plus 1 upon 2 1 minus 2n. Now cross multiply. We get 1 plus 1 minus 2n plus 1 plus 2n upon a plus b into a minus b is a square minus this b square. Now 2n gets cancelled. 1 plus 1 is 2. 1 minus 2n square is 4n square. Now 2 2s are 4 root 2 upon pi. This is 1 minus 4n square. This is our bn, an. Now we have to calculate bn. As it is, what is the difference between an and bn? Just replace sine cos by sine nx. This is the homework for you to calculate bn as it is like above. Just replacing cos by sine. Answer is 0. Okay. Therefore, Fourier series of this function is given by the equation number 1. This is equation number 1. Put this value of a naught, a and b and here. We get fx is equal to a naught by 2. This is a naught is 4 root 2 by pi. By 2 means divided by 2. Plus summation over this is an cos nx. bn is 0. No need to write this bn. This is 0. Okay. Now therefore put the value of fx. Original function is root 2 sine x by 2. It is under root of 1 minus cos x, which is equal to this term, is equal to the 2 to the 4, 2 root 2 upon pi plus take this constant outside. Constant with respect to summation means summation is over n. Therefore whatever apart from n, constants, pi and any other alphabet are constants, take that outside of this summation. We get 4 root 2 upon pi summation over this n cos nx upon 1 minus 4n square. Okay, this is both the side. Root 2 is a common. Cancel out this root 2. We get sin x by 2 is equal to 2 upon pi plus 4 upon pi into this summation. Now this is our answer for first question, Fourier series for this function. Now to prove that half is equal to summation over n. Now we have to prove this sub question by using our answer. Now if you observe this and this, what we get in this equation, what we will have to prove is this equation. In this equation 1 minus 4n square or 4n square minus 1 is same, but numerator becomes 1. That means for x is equal to, we have to put that value of x on the both sides so that cos nx becomes 1. And we know cos 0 is 1, and we have to vanish this. For vanishing this sign, we have to put x is equal to 0 on the both sides. Therefore, put x is equal to 0 in above equation. We get sin 0 0, 2 upon pi, 4 by pi, summation over n, 1 minus 4n square, cos 0 is 1. Therefore, 4 upon pi, this is equal to, this take this 2 upon pi out, that side minus 2 by pi. Now, summation becomes this pi comes to, pi gets cancelled, 4 upon 2, that is 1 by 2, minus 1 by 2. Now, multiply both sides by minus 1, minus take on that side, we get reverse this term only. Summation over 1 upon 4n square minus 1 is equal to half, which is what we have to prove. Okay, now let us see next example. Find Fourier series for the function. It is function is given in the interval form. Our interval, how we define our interval, the lowest number is 0, highest number is 2 pi. Therefore our range is 0 to 2 pi. and 0 to 2 pi is the range. Here suppose it is 0, this is 2 pi. Obviously the middle value should be pi. It is the angles, but we are calculating for comparison only. 0 to 2 pi, middle value is pi. That's why the interval is divided, or function is divided into two intervals. 0 to 2, 0 to pi, value of function is 1, and pi to 2 pi, value function is 2 minus x pi. It is the only difference. Okay, rest of the terms as it is. Now we have to find only Fourier series for the function. Now range of this series is 0 to 2 pi, therefore Fourier series is given by this. Call that equation number 1. Now a naught is 1 upon y integration 0 to 2 pi fx dx. Put the value of fx. Now function is divided in the interval, therefore 0 to 2 pi interval integration also divided into 2. First 0 to pi and then pi to 2 pi. 0 to 2 pi function value is 1, and pi to 2 pi function value is 2 minus x upon pi dx. Now take the integration. 1 integration is x from 0 to pi, rest of the terms as it is. 2 into 2 is a constant, integration of 1 is x, 2x minus again 1 upon pi is a constant, x integration is x square by 2 from the limits pi to 2 pi. Now put these values, upper limit and lower limit, we get this equation. A naught is equal to 1 upon pi as it is. This is upper limit pi plus 2 into 2 pi. Okay, first 1 upon pi as it is. Put the upper limit in the x, pi. Lower limit is 0. No need to write 0. Only pi is this one. Plus, now put the upper limit here, 2 pi. 2 into 2 pi minus 2 pi square by upon 2 pi. This is upper limit. Minus, put the lower limit bracket to the lower limit. Put pi in the lower x. We get 2 pi minus pi square upon 2 pi. Now simplify. Pi, this is 4 pi minus this is 4 pi square by 2 pi minus this is 2 pi minus plus pi square by 2 pi. 4 plus 1 5 pi minus this is 2 pi gets cancelled. 1 pi gets cancelled. 2 pi. This is again minus 2 pi plus pi by 2. Simplifying this, we get answer 3 upon 2. This is our a naught. Consider now an 1 upon pi integration 0 to 2 pi fx dx. Now again this integration divided into two interval 0 to pi and pi to 2 pi. In the 0 to 2 pi function value is 1 cos nx, plus in the interval pi to 2 pi function value is 2 minus x upon pi cos nx as it is dx. Now we have to, one integration is 1 into cos nx is cos nx, integration is sin nx upon derivative of nx should be divided, that is n, from the limit 0 to pi. Plus here we have to use u into v rule. This is arithmetic, this is trigonometry, this is u, this is v. U into integration of cos is sin nx upon n minus its derivative here. 2 derivative 0 minus 1 upon pi derivative of this bracket here into bracket its integration is here. Sin nx integration minus cos nx upon n, already n is there, it's become n square. Limit pi to 2 pi. Now again we know sin 2n pi is equal to 0, sin n pi is equal to 0. These are the values you have to mug up. Cos 2n pi is equal to 1, cos 0 is equal to 1, cos n pi is equal to minus 1 raised to n. These are the some values. Now put the limit sin, wherever sin is there in terms of pi, sin n pi is 0. This is 0 and lower limit also sin 0 0. Now here put the value of 2 pi here, it becomes 2 pi, pi gets cancelled, 2 minus 2 again here 2 n pi. So whenever sin is there, wherever sin is there for lower and upper limit, sin 2 n pi or sin pi 0. Therefore we have only this remaining term. Here's 2 minus this is the term pi to 2 pi as it is, minus 3 times minus, it becomes minus. Now put the value of 2 pi upper limit here, it becomes only this term, minus 2 cos of 2 n pi is 1 upon pi n square. This is only upper limit term, minus lower limit, put the bracket, again this is 0, minus cos of n pi is minus 1 raised to n upon pi n square. Okay, now again take this minus outside, minus 1 upon, take this pi n square outside, pi square n square, and it becomes 1. Again minus take outside, it becomes minus 1 raised to n. Now take this minus inside, reverse the term, minus 1 raised to n minus 1 upon pi square n square. This is a naught. Now calculate bn. What is the difference between an and bn? It is just a, instead of cos, it is only sine. These are the steps. Similar step, just only cos, instead of cos there is only sine. Just plus minus is there only. Okay. Now this is bn is equal to 1 upon pi n. Okay. Therefore Fourier series by equation number 1. This is our equation number 1. Put this value here. We get fx is equal to 1 a naught by 2. A naught is 3 by 2. By 2 means 3 by 4. Plus summation, this is an cos n x, plus summation, this is bn sin n x. Now take the constant outside. Whenever function is given in the interval format, then we write this fx as it is. You don't need to write fx here because fx is not a single function. It is divided into two functions. That's why write fx as it is. 3 by 4 plus this is 1 upon pi square constant outside of the summation, and this as it is, rest of the terms as it is, plus here 1 upon pi is also constant, rest of the terms sin n x upon n as it is. This is the answer for Fourier series. These are some homeworks for you. Fine. Question is same. Find Fourier series for the function for fx is equal to pi minus x by 2. And also prove that pi by 4 is equal to 1 minus 1 by 3 plus 1 by 5 minus 1 by 7 plus and dot dot so on. This is a homework. Answer for this question is range is same. In the range the whole chapter is depend on range only. Range changes, formula changes for the limits only, all rest are similar. Therefore 0 to 2 pi, a naught is 0, a n is 0, and bn is 1 upon n for this particular example. Fx is this. Fx contains only bn because a naught, a n 0. This is a n sin n x. Okay, answer. And for this second question, put x is equal to pi by 2 in this answer. Okay, you will get this answer. Now how to calculate f of pi by 2? Put here x is equal to pi by 2. Pi minus pi by 2. Pi by 2 by 2, that is pi by 4. On LHS side you will get this answer as it is in one step only. Now next, fx is equal to, again this is given in the interval format. X in the interval 0 to pi, 2 pi minus x in the pi to 2 pi. Solve as it is with the reference with the earlier example which is given in the interval format. What is the difference between the normal function and interval function? We have to just make the integration divide into two part only, that's it. The answer for this is a naught is pi, a n is this, and bn is 0 here. Okay, for in the Fourier series you can write down as it is these questions, this constants into coefficients into the equation number 1 for the Fourier series. We have generally write down there. Now consider next. Find Fourier series of fx is equal to, this is the biggest function, 3x square minus 6x pi plus 2 pi square divided by 12. This is the first question. Second sub question is also prove that pi square by 6 is equal to 1 by 1 square plus 1 by 2 square plus 1 by 3 square and so on. Depend on the answer of this question, we have to just prove this second sub question by putting the particular value of x on the both side of the Fourier series. Now let us start with the Fourier series. This is in the range 0 to 2 pi. Okay, now fx is given by this formula called that equation number 1. Now start with a naught is 1 upon pi integration 0 to 2 pi fx dx. Put the value of fx function here. Take this constant 1 upon 12 outside, and x square integrate x cube by 3, x integration x square by 2. 2 pi square is a constant, integration of 1 is x. Don't forget this step. Okay, limit 0 to 2 pi. After putting all the limits and calculations, the answer for a naught is 0. Okay, there are very simple steps. Now consider an 1 upon pi integration 0 to 2 pi fx cos nx dx. Now put the value of fx here. Take the 1 upon 12 outside of this integration. This is the term into cos nx dx. This is u, this is v, because this is a whole term is an arithmetic term, bracket. Call that 1 as a treat it as a 1 function, that is u, this is v. Okay, 1 upon 12 pi as it is, bracket, put the bracket, u into integration of v, integration of cos s sin nx upon n, minus its derivative here, 3 to the 6x minus 6 pi. Derivative of 2 pi square is 0 because it is constant. Okay, and sin nx upon n integration here. Sin nx integration is minus cos nx upon n. Already n is there, that's why n into n square, it becomes n square. Then next minus plus, plus minus, then plus. Its derivative here. Derivative of this bracket is 6 into bracket its integration here. Minus as it is 1 upon n square, that is as it is cos nx integration is sin nx upon n. That's why n into n square becomes n cube. Next step will be minus 6 derivative is 0. That's why u into v rule stops here. Limits 0 to 2 pi. Now whenever 0 or 2 pi, if you put in signed function, it becomes 0. That's why for lower and upper limit, sign terms get 0. We have only this, we have to only put these values in this cos function. Take minus minus plus, we get 6. Take outside x minus pi cos nx upon n square from 0 to 2 pi. Because sine 0 is 0, sine all term n pi to n pi, these are all 0. Okay, 2 n pi, we need 2 pi n pi. Okay, now put the upper limit. Take the 6 outside, we get 6 to the 12, 1 upon 2 pi. Put the value of first 2 pi in x, 2 pi minus pi, cos 2 n pi is 1 upon n square as it is. Minus now lower limit 0, cos 0 is 1, here 0, minus, put the bracket, minus, put this 0 here, it becomes minus pi. And this is the minus of lower limit divided by this n square as it is. Now pi minus minus become plus pi n square, plus pi upon n square become 2 pi upon n square. It's 1 upon 2 pi as it is. 2 gets cancelled, pi gets cancelled, 1 upon n square is our an. Now bn. What is the difference between bn and an? Just replace cos nx by sin nx. Rest of everything is same. These are the steps. U into v rule is same, everything is same. Just brackets, sign integrations are only difference. Okay, by sorting this we get the answer 0 for bn. Okay, now these are the constants a naught, an and bn. But therefore Fourier series form equation number 1, it becomes fx is equal to summation, only an is exist 1 upon n square cos nx. bn is 0. No need to write 0, you can directly write down 0. Therefore fx is given this is equal to summation over n 1 upon n square cos nx. This is the answer for first question, Fourier series. Now to find out the prove that question, what is the prove that question? Prove that pi square by 6 is equal to 1 upon 1 square plus 1 by 2 square plus 1 by 3 square. That series comes from this series. For that, if you go on putting the 1, 2 and 3, summation over n means put the value of n is equal to 1, 2 and 3 and go on adding those terms. For that cos should be vanished, therefore that we know cos 0 is 1, therefore put x is equal to 0. It depends on the series, what series we want. Okay, put x is equal to 0. This is our pure guess. Therefore not every example containing this step every time you will get the same answer by putting x is equal to 0. No, in the particular example by putting x is equal to 0 we get this answer. Okay, but therefore put x is equal to 0 in above equation, we get this is 0, this is 0, 2 pi square by 12, this is equal to cos 0 is 1 upon n square over the summation. Therefore 2 6 is 12, pi square by 6 is equal to 1, putting n is equal to 1 upon 1 square plus 1 by 2 square plus 1 by 3 square plus 1 by 4 square and so on. This is the required answer. Let us see next. Find Fourier series of function f(x) is equal to pi square minus 2 pi x plus x square divided by 4 in the series 2 to 2 pi. First question. Also prove that these are the three standard uh, um, um, series. Pi square by 6 is this, pi square by 12 and pi square by 8. We have to prove these three using this Fourier series. Okay, this is the similar kind of example like earlier one. That's why this is the homework for you. Fourier series, just finding out the Fourier series is the homework for you. Fourier series is given by this formula, call that equation number 1, and we know what is a naught, an and bn. For that, this is a homework, and I'm directly given you the answer for this thing. Fx is equal to this as it is, a naught by 2 pi square by, answer is this, pi square by 12 plus summation over n. An is 1 by n square, it becomes 1 by n square cos n x, supposed to be bn equal to 0 here. Okay, this is the answer for Fourier series of fx, call that equation number 2. Now we have to reduce these things. First of all, put x is equal to 0 in above equation. What we get, pi square, this 0, it is 0, pi square by 4 is equal to pi square by 12 plus summation over 1 by n, cos 0 is 1 upon n square. Now take this pi square by 12 on the LHS side. Pi square by 4 minus pi square by 12 is equal to, put when value 1, 2 and expand this series, we get this. Pi square minus pi square, take common, 1 by 4 minus 1 by 12 is pi square by 6, and this is the answer. Okay, first we have got this. Now for second, this one, obviously we should put this value other than 0. Okay, put x is equal to pi in the answer 2. What we get, pi square minus 2 pi square plus pi square divided by 4. Put x is equal to pi here, is equal to pi square by 12 plus summation over n, 1 upon n square, cos of n, a value of x is pi. Now we have to reduce this example. Pi square minus 2 pi square, 2 pi square, 2 pi square gets cancelled. Answer is on LHS side 0. Pi square by 12 plus summation over n, cos of n pi value is, we know, minus 1 by minus 1 raised to n here. Okay, now take this pi square by 12 on this side, we get minus pi square by 12 is equal to minus, put the value of n first 1, minus 1 raised to 1 is minus 1 upon 1 square, plus put n value 2, minus 1 square is plus 1 upon 2 square, plus n value 3 minus 1 cube. Whenever odd numbers are there, it becomes minus. For even number, we have minus 1 raised to e1 is plus 1, and so on. Okay, multiply on both sides by minus, we get pi square by 12 is equal to this plus minus plus minus. This is what we get for the second question. Now third one, pi square by 8, we can get it by adding these first two. Okay, adding series 3 and 4, we get pi square by 12 plus pi square by 6. Call this series first 3 and this is series 4. Now adding these two means LHS side adding, RHS side adding, we get pi square by 6 plus pi square by 12 is equal to, this is series for pi by square by 12, this is the series for pi square by 6. Now if you observe this, 1 upon 2 square minus 1 upon 2 square gets cancelled. 1 by 4 square minus 1 by 4 square, whenever even terms gets cancelled. Okay, and odd terms, 1 by 1 square plus 1 by square are 2 times. 1 by 3 square, 1 by 3 square 2 times. Therefore it becomes 2 times 1 upon 1 square plus 2 up times 1 upon 3 square plus 2 upon 1 plus 1 upon 5 square, and so on. These are the odd remains only. Now it becomes pi square minus pi square by pi square by 12 plus pi square by 6. Pi square gets common, 1 upon 12 plus 1 by 6 is 3 pi square by 12 is equal to this is the thing. Now divide throughout by 2, and this, take this 2 in this term, 3 4 is 12, and again 2 take common, and 4 to the 8. Pi square by 8 becomes, this is the 1 by 2 to 1 square plus 1 by 3 square plus, and so on. This is the last series we are getting directly by adding first two series. Okay, now this is the example for homework. Find Fourier series of the function f(x) is equal to pi minus x upon 2 in the range 0 to 2 pi. Also prove that this is the answer. I think This is the repeat example. Okay, we have already repeated. Okay, no need to write down this. Already it is given. These are hints given in this example. Okay, in earlier example I have not given hint. Solve that by using this hints. This is a repeated example. Okay, these are the some examples we have seen. First point of this Fourier series in the range 0 to 2 pi. Now we are going to change the range. Fourier series we are going to see in the range minus pi to pi. Okay, and whenever there is lower limit minus upper limit plus same number, okay, then we have to see whether the given function is even or odd. If function is even, then bn directly write down 0. No need to calculate bn in this range. Okay, in the range 0 to 2 pi we have to calculate all the constant coefficients a naught, an and bn. But whenever there is a certain range where lower limit is minus, upper limit is plus same number, then we have to whatever the number, it should be minus 1 to 1 in and later on we are going to see the minus 1 to 1, minus 2 to 2 range, these types of range. Whenever there is lower limit minus, upper limit plus same number, then we have to first step will be whether the function is even or odd. Okay, some functions are neither even neither odd, we are going to follow the same formulas. Okay, if function is even, then bn 0, directly write down bn 0, and a naught is this 2 upon pi 0 to pi fx dx. An is 2 upon pi 0 to pi fx cos nx dx. Bn is 0. And if function is odd, then a naught is 0, an is 0. Only we have to calculate bn is 2 upon pi integration 0 to 2 pi fx sin nx dx. Okay. Now how to remember these formulas when to bn is 0, when a naught is 0. Remember, whenever bn is 0, only one coefficient bn is 0. Whenever a is there, then both the an and a naught is 0. And remember from this, from one shortcut is there, if fx is odd contains o, and a from the both of the a naught, this contains a naught. We don't have b naught. Okay, that's why you can write you can remember like this. If function is odd means o, where is o in a naught is only o. That's why a naught ends with a naught, an is also 0. Okay, when function is even, bn 0. Okay, and bn is write down bn is like this. It is an and bn and same, just replace cos by sine. Okay, simple questions, simple formula. Now let us start with the function. Example, find the Fourier series for the function f x is equal to x square in the range. Now range is different, minus pi to pi, and prove that these are the same entities, same series, pi square by 12, pi square by 6, and pi square by 8. Again same thing, pi square by 8 can be added by adding these two. Okay, first we have to find out Fourier series for the function in the range minus pi to pi. For the range of minus pi to pi, lower limit is minus, upper limit is plus. We have to decide whether the function is even or odd. But obvious, fx is a x square, it is a even function. For that, how to calculate even function? Range is minus pi to pi. F of put x is equal to minus x on the both side. We get f of minus x is equal to minus x square. We know minus x square is plus x square. We get the original function fx. F of minus x is fx. Therefore, fx is a even function. For even function, directly write down bn is equal to 0. Okay. Now calculate a naught by this formula, 2 upon pi integration 0 to pi fx dx. Put the value of fx as x square integration x cube by 3. Put the limit 0 to pi. Here we get pi cube by 3, lower limit is 0, no need to write 0. Calculate that, we get 2 pi square upon 3 a naught. Now an is 2 upon pi integration 0 to pi fx cos n x dx. Put the value of fx x square cos n x dx. Again u into v rule should be applied. 2 upon pi as it is, u into integration of cos is sine minus plus sine nx upon n minus x square derivative here, 2x into this bracket sine nx integration is minus cos nx upon n, already n, that's why n square. Again plus plus minus plus 2x derivative here 2, and its integration here sine nx cos nx integration is sine nx upon n, already n square is there, that's why n cube, and minus as it is because it's a constant. Okay, and next term will give minus 2 derivative 0. That's why u into v rule stops here, limit 0 to pi. Now we know sine 0 is 0 and sine n pi is again 0. For the both the limit, upper and lower limit, sine terms gets cancelled. Therefore we have to concentrate on the middle cos term. Minus minus becomes plus. It becomes 2 upon pi 2x cos n x upon n square from 0 to pi. Both the sine term we are cancelling here because we know sine terms gets vanish for pi 2 pi 0 limit. Now you can write down here sine n to n pi is equal to 0, sine 0 is equal to 0, sine n pi is equal to 0. Okay, now take 2 common, 2 to the 4 upon pi n square outside. We are putting the limit pi into x, pi into cos n pi is minus cos 0 is 0, cos this is x, I put the value of x here, is equal to 0, we get 0, lower limit. Now pi gets cancelled, cos of n pi is minus 1 raised to n, 4 into minus 1 raised to n upon this n square is our an. And bn is already 0, therefore Fourier series is given by fx is equal to a naught. Here a naught is this 2 pi square by 3 divided by 2, that's why 2 gets cancelled, pi square by 3 plus summation over n, this is an cos n x. Bn is 0, no need to write 0. Therefore fx is function x square, this as it is. Take the 4 constant outside of the summation. Now these are the homeworks for you. For this pi square by 12, put x is equal to 0 in this, you get this. Put x is equal to pi, you get this pi square by 6, and addition of these two you will get pi square by 8 by earlier example, you can refer that.